We're now going to do part one of reactions of carbonyls. Now that's going to be to do with alcohols and oxidizing alcohols to aldehydes, carboxylic acids, ketones, and showing that tertiary alcohols don't actually oxidize. We'll take you through how to do the balanced equations, and we'll also take you into the lab and we'll show you how you actually do these reactions in the lab. First thing is you have to recognize whether alcohols are primary, secondary or tertiary. So let's have a look at propan-1-ol. Propan-1-ol, let's look at this carbon that's bonded to the OH. How many groups are coming off that? One group coming off that, and it's that carbon there, and therefore one group means it's primary. Look at our next example, which is propan-2-ol. So let's look at that carbon again, that central carbon. Look at the groups that come off. There's one there and there's two there. So that would be a secondary because it has two groups connected to the carbon that's connected to the OH. We then have our tertiary. Now, our tertiary is going to be this carbon again, and then we look at the groups that are attached. So it's 1, 2, and then 3. 3 groups means it's tertiary. And you can easily recognize that if you're looking at skeletal formula, because skeletal formula, it just depends on how many lines are going to that carbon. So count the number of lines, that's the number of groups. Let's now go into the oxidation itself. So we want to oxidize it using an oxidizing agent called Cr2O72- /H+. Now that is potassium dichromate with sulfuric acid, sometimes called acidified potassium dichromate. And that will take it from a primary alcohol to an aldehyde. And that is the easiest way to remember the oxidizing agent. When you're asked for the reagents, the reactants, that is what you need to put down on the page. But it can be represented as O to do balanced symbol equations, which we're going to show you now. But remember, when you're doing the reactants, the exam tip is you can use any of those words. You can do Cr2O72- /H+, or you can do acidified potassium dichromate, or you can do K2Cr2O7 /H2SO4. But before I go through the balanced symbol equation and how to do it, I'm going to take you into a lab and use a different example of how I can make an aldehyde from a primary alcohol. So we're now in the lab to do oxidation of a primary alcohol to form an aldehyde. The primary alcohol we're going to use is 2-methylpropan-1-ol, and we're going to use dichromate, the Cr2O72-, which has this vivid orange colour, which you have to remember. Now this orange colour, when it is oxidizing the alcohol, is going to go to green. And hopefully you'll be able to see green when you look at this reaction which we set up here. So what we've got here is our dichromate, our alcohol in there, and we're boiling it, and it is evaporating up the tube. Now, here's the important thing. I'm going to show you some boiling points, and as you can see, the aldehyde has a boiling point of 63 degrees Celsius, whereas the alcohol and the carboxylic acid, which are the other two reactants and products that can occur in this, they are higher, 108 and above. So that means as long as we boil this to below 108, we'll only collect aldehyde. And the reason is because aldehydes have permanent dipole-dipole attractions between them, and they are weaker than hydrogen bonds. And the alcohol and the carboxylic acid have hydrogen bonds, therefore the boiling point is higher. So we can use that to our advantage to be able to get the aldehyde off because it has a lower boiling point than the other two. So if we then look at this, we can see it is evaporating, going up the tube, and we can see that our temperature that we've got on our thermometer is less than 108. So we are only going to collect the aldehyde. And then if you look here, it is condensing down this tube in the condenser, and then it is turning into a liquid in the ice bath. And the ice bath is just to make sure none of it escapes as a vapor. Now that is how you distill to make an aldehyde from a primary alcohol. And now we're going to go back into the studio to show how this can be drawn and done in the style of an exam question. We've now seen an example of how you can use an alcohol, okay, and turn that into an aldehyde using the apparatus in the lab. And later on in this video, we'll show you how to draw that in the style of an exam question. But first of all, let's show you how to do the balanced chemical equation. So the balanced chemical equation is going to use the oxidizing agent as O, and you'll always see that in your exams, in those square brackets. Now, it turns into an aldehyde. So an aldehyde, if you remember, and again, try and draw this before I do it on the video, or stop the video. And you can see that is your aldehyde. So you've turned your propan-1-ol into propanal over there. All you have to do now is look at the hydrogens that have been removed from this propan-1-ol compared to the aldehyde. So if you do that, just count the number of hydrogens on that side and count them, and you'll find that there are 2 missing. Now the 2 missing are these 2 hydrogens here, okay, and that hydrogen again is connected to this carbon, and then the other hydrogen is connected, as you can see over there, to the oxygen, and they've been removed. Because there's 2 been removed, they're still around the oxidizing agent. So the oxidizing agent oxidizes the hydrogen. Oxidized hydrogen is called water. So if we oxidize that water, or oxidize that hydrogen, sorry, you'll get 1 water. That's because there's 2 hydrogens, and 2 hydrogens is needed for 1 water. So therefore, in this entire process, we will get 1 oxidizing agent and 1 water produced. Now it's really important, if you do the reactants and the conditions for this, you say that we distill as we did in the lab, okay? And it's really, really important, it takes a primary alcohol through to an aldehyde. And like I say, 1 oxidizing agent and 1 water produced for that reaction. So we use up 1 oxidizing agent and we make 1 water. And just to remind you again, remember that colour change, orange to green. I know in the lab it looks so dark it's hard to see the green, but it's orange to green is that colour change. Now we're going to do primary alcohols to carboxylic acids. Now to do that, you need to reflux, and we'll show you in the lab what reflux is soon. But first of all, you take a primary alcohol again, you add it to your oxidizing agent, and as you can see here, we've got our aldehyde, and we've got this water. Now, if we reflux it, all of the aldehyde is still near to the oxidizing agent. We do the distillation to separate the oxidizing agent from the aldehyde, or the aldehyde from the oxidizing agent. But if it's reflux, they're all stuck in the same place. Therefore, it continues to oxidize. And it will oxidize using another mole of oxidizing agent to the carboxylic acid. Now, the really important thing is how many more waters are produced. So you do this again by counting the hydrogens as you go along. So count the hydrogens here, and you'll find there are 6. 1, 2, 3, 4, 5, and 6. And then if you look at this one, there's also 6. 1, 2, 3, 4, 5, and 6. So no hydrogens have been removed, therefore no extra water is produced. And if we take this all into account, we take the 2 oxidizing agents, okay, and we take that 1 water, and then we get rid of the intermediate because we don't need it, because it's just going to go all the way through to the carboxylic acid, you'll get this overall equation. So 2 oxidizing agents to make this happen, reflux to make this happen, okay, making your carboxylic acid plus water, with again your orange to green is your colour change, again your Cr plus 6 going to your plus 3. And it's really, really important if you're doing this that you know how to do primary alcohols straight to carboxylic acid. So you want to go to aldehyde, it is distillation. You want to go to the carboxylic acid, it is reflux, but it's the same conditions. Cr2O7 2- and H plus, or acidified potassium dichromate. Remember, in this occasion, 2 oxidizing agents and 1 water. Next one we're going to do is ketones. And I want to show you in the lab this time how this works, because secondary alcohols going to ketones also uses reflux. So by using reflux to do this, it's also the same way as if you would do a carboxylic acid. So if you go into the lab right now, and you'll see how both ketones and carboxylic acids are made using reflux. Now, the example we're going to do is the oxidation of a secondary alcohol, propan-2-ol. So we have propan-2-ol here. See, it's a colourless liquid. And then we have our oxidizing agent. Our oxidizing agent is acidified potassium dichromate. You can see this is orange. Okay, you will need to remember that colour change that we have during this experiment, and it is cancer causing, hence I've got gloves on. Okay, and it's really important if you do this in the lab, you've got the lab coat, you've got the goggles, and you've got your gloves on. We're also going to use anti-bumping granules to make sure the liquid doesn't bump up the tube. So what we have is propan-2-ol, and we can represent our oxidizing agent with square brackets and O, and then that makes our ketone and also makes water. And that's your balanced chemical equation that I would expect in the exam for this reaction. Now let's move on to the actual condenser itself. If we're drawing this, we're going to have to label the condenser, we're going to have to label the round bottom flask, and when we go into the next version of this, when we're heating it all up, we'll have to label the heat as well. But before I do that, I want to show you the water in and water out. So the water in is at the bottom, and what happens, and I'll show you right here, is as I put the water on, you'll see that the water goes up, and then it forces all of the air out. And that's what you want it to do. And I'm going to put it on a bit stronger just to force all of the air out. There you go. You can see all that water is now forced out. And then I'm going to put the flow right back down so it's really, really small. And you can see this outer kind of casing is full of water now. So it's very, very cold. And there's no air bubbles. And that's why we fill it in from the bottom. So if you're doing the exam, water in from the bottom, water out from the top. So what we're going to do now is we'll put all of our chemicals into our reflux apparatus and show you the full setup. We've now done the whole reflux setup. You can see that we have our heat-proof mat, we've got a tripod and a water bath. And you often use a water bath. You can also directly heat it with a Bunsen burner, but you have to be really careful with that. And we are heating it using that Bunsen burner to get this evaporation and this condensation. So it's evaporating from here, and then you can see it condensing as well. Now, really important thing is that when you're drawing this in the lab, you can draw that Bunsen burner as an arrow and just write heat by it. You don't have to draw the Bunsen burner, and then obviously you have to label the round bottom flask and the condenser and your water in at the bottom, water out at the top. Okay, but the really important thing here is that why do we do this reflux? We do this reflux to make sure that the reactant doesn't get away from the oxidizing agent, so it's fully complete, the reaction is fully complete, and we also do it so that the solvent can't escape because it evaporates and then condenses, and solvents are often flammable, so it's much, much safer to keep the solvent trapped within there. And those are two reasons why we use reflux. In this case, we want to push that propan-2-ol all the way up to propanone. We want all of it to react. So therefore we choose reflux to keep all of those reactants together. What we're going to do now is take you back to the studio, and we will show you this in the form of an exam style question and answer. Now you've seen how a reflux happens inside the lab, let's again go through that balanced chemical equation. So to make the ketone, you need an oxidizing agent. The oxidizing agent goes to the ketone notice. Here we have this hydrogen that is missing and this hydrogen that is missing. Just look over there, you'll see both of those hydrogens are missing. Because of that, they've been removed, so that's why you get two hydrogens and you make your water. So when you take a secondary alcohol to a ketone, it'll be one oxidizing agent and it will be one water. And remember, as ever, as we've seen in the video as well, you'll get that orange to green colour when you use acidified potassium dichromate. Now, we're now going to do tertiary alcohols. Now, tertiary alcohols, there is no oxidation as there are no hydrogens to leave. Now, what does that really mean? So if you look here, I can see there's a hydrogen here which could potentially leave, but I can't see any other hydrogens that are directly on this carbon. And you need two hydrogens to leave to do an oxidation of an alcohol to go up to a ketone. And that's the only way it could go because it's got two R groups either side for the ketone. So even if you add the oxidizing agent, you'll find that nothing actually happens because there's no hydrogens on that carbon. And the only hydrogen that can be removed is this hydrogen on the H, and you need two, not one. So nothing happens no reaction happens, and so the colour stays at orange because it is +6 in the Cr2O7 2-. So that means chromium-6 being orange doesn't change colour at all because there's no reaction occurring. Now that we know the different reactions of primary, secondary and tertiary alcohols, it can actually be used to differentiate between them. And we will go through exam style questions on that in other videos. But first of all, it's really important that you know this exam tip. And it's just based upon these colour changes. So if you look here, the primary colour change will always be orange to green because you're going to take it to the aldehyde and then possibly to the carboxylic acid. Remember, the aldehyde is distillation, the carboxylic acid is reflux, okay, it's depending on the conditions. You then go to secondary alcohol, again, reflux, always with a secondary alcohol, but that will again go from orange to green, go from that +6 chromium oxidation state to that +3. And lastly, the tertiary, there'll be no colour change as it will stay orange because there'll be no oxidation happening at all. So therefore, that means clearly you can differentiate tertiary from secondary and primary because it will not react. There's a difference in colour changes. But again, we'll go through that in an exam style question in the next few videos.